Marko Aunedi, who is a research associate in the Faculty of Engineering at Imperial College, London in the UK. His research focuses on the generation scheduling under uncertainty, so it's the power generation. And he'll talk to us today about the effect of electric vehicles on, I guess, sort of power generation capacity. So coming at it from a very different perspective from the vehicles, coming at it from the perspective of the power generators.
Thank you very much, Mr. Chairman, Your Excellencies, ladies and gentlemen. It's a pleasure to have an opportunity to present here. So as I was introduced, I don't come from the transport or automotive sector. Our expertise is primarily in electricity systems. So just a few words about where I come from. So I come from London, a place called Imperial College. That's a university which has a very, very good international reputation when it comes to science, technology and medicine. And within Imperial, our group is doing research in various aspects of electricity system economics, integration of renewable energy, etc. So the question we are trying to answer when it comes to electric vehicles and electrical mobility is primarily what is the impact of large-scale EV rollout on the performance of the power system. Or to maybe give an example, for instance, if a lot of people buy electric vehicles, if they start to charge them when they come home from work at 6 o'clock, that would create a huge peak demand on your network, and you might have to reinforce your distribution grid, put thicker lines with more transformers, and that will cost money. We also try to see what is the value of doing this a bit smarter. So if you are able to do smart charging, if you're able to distribute the EV demand, how much cost savings that will achieve, and also how much potentially CO2 savings that would incur. So, why EVs? Why we think EVs are interesting to investigate in this sense? So, as I said, adding EV demand onto the existing electricity demand will have certain implications for how much generation and network capacity you would need to provide. What we typically see is that if we don't apply any smart charging schemes, if we just let people charge whatever they want, you would typically see a significant increase in the peak demand of the system, and that will of course require some cost. On the other hand, we see that vehicles are typically stationary for a large amount of the time. Of course, that's unless you're a taxi driver. But for most of residential customers that commute to work and back, you see the vehicle being stationary for 90% of the time or even more. So that suggests that if they have an electric vehicle, that there could be significant flexibility in terms of when this energy is actually delivered to the vehicle. So it doesn't necessarily have to be right exactly after they plug in the car. It could happen a bit afterwards. They will still have enough energy in the battery to undertake all their intended journeys, so there wouldn't be any compromise on their mobility. And that would, of course, be a much cheaper proposition. What's especially relevant for the European context, and we've been involved in quite a few European projects looking at these issues, is combining electric vehicles as one policy to decarbonize the energy supply, and on the other hand, deployment of renewable energy as a second important pillar of this policy. So combining, of course, renewable deployment with EV rollout is something that makes perfect sense, because if you put EVs in a system which is mostly based on fossil fuels, then of course the CO2 improvements will not be as dramatic as if you put them in a system that's mostly based on technologies like wind or PV. And this, let me just see if I can get the pointer. Is there a pointer on this? Hang on. So here you can see that for the typical UK driving patterns, this is the percentage of vehicles that are stationary at a given point in time. So you can see that most of the time this is about 80%, and overnight it's actually close to 100%. So that kind of gives us an indication that there could be flexibility in terms of how this EV demand is actually met. Among other things, we have been involved in some of the biggest EV trials in the UK, which monitor driving patterns and also the charging patterns of various types of electric vehicle users. And here I'm just showing a few examples of what kind of the average charging profile for an average day would look like for a residential customer. So it's not surprising to see that this peaks around evening hours, so after 8 o'clock, when people come from work, plug in their cars and just leave them until the battery is full again. On the other hand, the trial also observed a fleet of commercial vehicles, and for those vehicles the situation is much more heterogeneous. So depending on what the use of the vehicles are, what the use of the vehicle is, you would see markedly different patterns. So this example is for a fleet of commercial delivery vans, so something like UPS or DHL. And what they have is typically almost zero charging during the day because all the vehicles are outside doing their deliveries. But then once the working hours finish, they come back to the depot, start charging. You see this huge increase in charging power. So that's something that the local grid might have difficulties to supply, something to have in mind. And also from this trial we were able to elicit what the diversity of say residential EV demand would be. So of course if you had only a small number of electric vehicles, their peak charging is much more likely to coincide than if you have a diverse pool of vehicles that some of which charge earlier, some of which later, but you see a lower ratio between the aggregate peak across all vehicles and the sum of individual peak for each vehicle. So this situation is of course better for the grid than if you have a lower diversity. Another example for the UK, a study we did for the 2030 system, assuming a significant deployment of renewables. The question was how would this energy balance look with and without what we call the smart charging. So depending on how the people drive, we allowed our model that we developed for this purpose to shift this electric vehicle demand so that the cost from the system perspective is minimized. So if you don't do that, if you just add EV demand as it would happen, as we've seen in the previous chart, with a peak coming on in the evening when the rest of the system also has peak demand, then you can see that you've got a huge increase in peak on top of the existing demand. And that will of course require a lot of investment in infrastructure. So we need to add more generation capacity to supply these peaks and also additional network capacity to supply the same peaks. Plus you would also probably need to use very expensive peaking generation units to supply these peaks. So overall this is quite a costly diagram for the system to meet. On the other hand, if you're able to do smart charging, if you're able to move some of this demand away, you can see that the cost is minimized by moving some of this demand into night hours, and you can see that the overall resulting demand profile that the generation fleet sees is much more flat, and this is of course a much cheaper way to supply your demand if you're able to do smart charging. This is an example for a winter week, and similarly we also have an example for the summer week. Now in summer you might have a problem, especially in the UK context, if a lot of wind is built and you have wind output peaking during the night. So if you have high wind output combined with low demand, what you might need to do is curtail wind output, basically shut down some of the wind turbines because you just can't absorb all of that electricity. And that's of course very bad because you're spilling basically zero carbon and zero variable cost electricity. So that's something which would need to be avoided if at all possible. But if you're able to do smart charging, if you're able to shift EV demand around, you would again fill the valleys you see during the night, and you would potentially avoid having to curtail wind. And just to zoom in a bit on those couple of days, you can see these bits that become negative. So this is what we call net demand. This is the difference between system demand and wind output. So if the wind output is higher than system demand, you get into negative territory, which would then mean you would potentially have to spill wind. Now, if your EV demand, which looks like this, if it's non-smart, so only peaks in the evening, if you're able to shift it around, then you would move a lot of this during the night, and you would you'll be able to avoid having to curtail them. But we also see that with increasing EV penetration for this particular system, the overall curtailment of renewables, the overall spillage of renewable output that we see in the system would drop significantly if these cars are operating in a smart way. So the cars greatly help, smart EV charging greatly helps to have an efficient integration of renewables as well. So these two are quite linked together. I'll just say a few words about a very big and interesting project we have been involved in up until February this year. It's been funded by the European Commission. It's called Green Emotion. There's a website here. Probably some of you are already familiar with it. It was quite a big project with over 40 million euro budget and quite a frightening number of partners. Honestly, it's 43 partners. So the coordinator of this project had quite a hard job to actually keep everything in place. But the project has been finalized in February this year. There's a large number of reports and other materials available on the website. I've also included some links at the end of this presentation, which I hope will be distributed later on, so you can have a look at more details if needed. But basically, what this project tries to do is address electromobility in Europe across the whole a broad spectrum of dimensions. So ranging from standards and interoperability of the ICT infrastructure down to how would the roaming in Europe look. So for instance, if you're an EV owner that lives in Italy and you want to drive to France, how would you be able, in practice, to charge a vehicle in France? You would need to have some communication that recognizes you, your contract with the local provider, similar to the mobile phone roaming concept. So those are the things that we looked at in the project. There's also a lot of work done on policy guidelines for the policymakers, how to speed up, how to incentivize the uptake of electric vehicles. And also, last but not least, there was a significant data collection effort undertaken in 10 European demo regions across different countries, Spain, Italy, France, Denmark. And a lot of data was collected and summarized to potentially provide some insights and also to provide learning points for the policymakers in terms of what the cars will actually do if they are deployed. Now, our Imperial's analysis within the project focused on the impact of different EV charging strategies on the electricity system. So that's where expertise lies. What we try to do now is adopt what we call a whole system approach to see what's the actual cost if you deploy EVs, and if you try to estimate this cost across all of these categories. So operating generators, building generators, building the network, cost-efficient distribution, and also estimating the carbon emissions from the system. And with the overall goal to inform the policymakers, providing with the evidence of what different approaches to EV integration would mean for the cost and for the emissions. This is just a quick overview of the model that we used. So we used an entire European grid model. We also used what we call the representative distribution network, so we can quantify the impact both on the high voltage side and the low voltage side. We plug all of these data into the model, and the outcome results were how much capacity we need to build in the system, how we would operate it, what would be the curtailment of carbon emissions, and that enables us to quantify the benefits of smart EV charging by comparing the system without a smart charging and the one with. As part of our involvement in this Green Motion project, we've also developed a tool, a relatively simple but still very useful calculation tool for estimating the reinforcement cost of low voltage distribution grids that see a large uptake of EVs coming onto the grid. This tool is called ITRES, and it's publicly available on the Green Motion website, so it can be freely downloaded and used. There is the tool itself, and it's also accompanied by the user manual and some calculation examples. So whoever is into estimating the impact of EVs on the LV networks would find this quite useful. And just as an example of the outputs of this tool, it can tell you, in the non-smart world, how much you would have to invest in your network across the year. So these different colors refer to different network component types. So that could be overhead lines, underground cables, transformers. So this tells you that you would have to invest quite a lot over your planning period if your EVs are non-smart. But if your EVs are smart and your peaks are lower as a consequence, then you would have to invest a lot less. And now coming on to the actual cost implications on the overall system for EV integration. What we see that if we have what we call business as usual or non-smart, so just let the vehicle owners charge when they like, we see that it would cost around 200 euros per EV per year to supply this additional demand. Out of these 200 euros, around 140 would come from increased operating costs, because this is additional energy we need to provide, so we would need to burn more fuel somewhere, and that would mean higher operating costs. The red component here is the additional generation capital expenses. So we need to invest in more generation capacity to meet the increased peaks. And similarly, the yellow component is the distribution network investment. So we need to invest more in the distribution grid as well, for the reasons shown in the previous slide. So we can see what the breakdown of this additional cost per EV is in the non-smart case. If we then move up towards the smarter cases, and we have here two smart cases, we call them smart timing and fully smart. The difference being that in the smart timing case, you can shift your demand around, but that's about it. Whereas in the fully smart case, we also allow electric vehicles to provide some balancing services to the system, so something like reserve and frequency regulation. But the key message here being that if your vehicles are smart, if your EV charging schemes are smart, you're able to cut down the cost, the additional cost of supplying the EV demand by half or even more. So our studies show that the more flexible the vehicles are, the less you would need to invest in your system, and the cheaper the system would be to operate. So you save, for instance, you can see that the distribution capex component completely disappears, because now you're able to shift your demand and avoid increasing the peak. Similarly, you reduce significantly the generation capex component, and you also reduce how much operating costs it will require to supply the EVs. And we find the similar trends across different penetrations of EVs, and also across different European systems. Now, just to maybe make a disclaimer here that in this study we just assumed that a certain number of EVs are available in the European systems. We didn't worry, so to say, how these vehicles would actually come on, what policy instruments we need to make this materialize. So we just tried to look at what if we had this number of vehicles, how much more would it cost to supply them. Then in addition to cost, we also looked at what will be the implications for the environment. So what we found was that if your vehicles are becoming smarter, then the percentage, the utilization of your renewable output increases in all of these four systems that we looked at. So these would be, this is UK with the Republic of Ireland combined, Spain, Italy, and Denmark Germany with Denmark combined. So in all these systems, and the UK probably being the worst because it's an island system, we see that EVs help the most in terms of absorbing the renewables. This is a very interesting chart because it shows when we add EV demand onto the system, how much more do we emit of CO2, and we've expressed these additional emissions of CO2 in grams per kilometer driven to make them comparable to the statistics that manufacturers publish when they have to declare what the emissions of their vehicles are. So we see that in all systems, even in the business as usual case, even without smart charging, the additional CO2 emissions are between about 25 and 40 grams per kilometer, which is, of course, a lot lower than what, for instance, the 2013 average emission is for the European fleet, around 127, and as well as lower than the target which is set for 2021, which is 95 grams. So this shows you that even in this non-smart case, the CO2 effect on overall is positive. So of course you reduce the CO2 emissions from these vehicles to zero, but of course that CO2, that energy has to come from somewhere, and of course because you have to produce this additional energy, you would incur some additional CO2, but not as much as you have displaced by making those cars fully electric. Now the question is, this number could of course be a lot higher. This number depends on what your generation mix is. So if your generation mix is based on fossil fuels, for instance, at a very extreme case, if you only got coal generation, then this would probably increase to, say, I don't know, 150, 180 grams. So it seems that from the CO2 point of view, this makes sense if, and this is also here, all these systems have an ambitious deployment of renewables in terms of wind and PV. That seems to be the message from this. Just to wrap up with some key findings. So, as I shown, the additional cost of supplying an EV has been around 200 euros per EV per year. But if you're very smart, you can reduce this by 50% or even more potentially. Now, some of the future challenges we see, and that also provides a direction for further work, is that this is all theoretical. This is all based on minimal cost. The question is, what kind of regulatory system, what kind of market arrangement, what kind of supply contract you would need to have in place for this to happen? Because if you're an EV owner, how would you actually earn money, or how would you benefit, say, in terms of reduced electricity bills, if you decide to participate in the flexible demand schemes? That area still needs some work, both in terms of research and in terms of developing regulatory framework for that. What we also see is an interesting problem that we're in a project that's supposed to start soon, is the fleet vehicle concept. So some niches of vehicles tend to be probably more prone to be early adopters of EVs because they see a large annual mileage. So, for instance, delivery fleets, that's a good example of that. So the question is how they would, what impact the fleet vehicles would have on the local electricity infrastructure. So as we've seen in one of the earlier slides, if they all start charging at the same time, they might produce quite a high increase in loading of the grid. So the question is whether we can manage that at the level of let's say, single fleet operator. And also the question is whether, if we aggregate the vehicles that are operated by this operator, whether we can perhaps sell and provide some services to the system as a whole, to the grid operator. So to provide, let's say, flexible reserve or frequency regulation, because that could be a potential source of additional revenue for the operator. This is just a list of reports that go into much more detail about all of these things. Whoever is interested, I very much encourage you to read. And with that, I'd like to thank you for your attention, and I look forward to answering any questions you might have. Thank you.
Thank you very much indeed, Marko. Any questions for Marko at all? Yes?
I'd like to ask regarding the smart, you're talking about this being part of the smart system. Sorry. You're talking about the smart systems being part of the EV itself. So is this a standalone system, or would you require that the existing infrastructure is also smart in a way, or could this be a standalone solution?
I would say there would have to be an interaction between the EV and a party which knows the conditions in the system. So whether that would be a distribution network operator, or that would be a third-party provider like an aggregator. I think the intelligence would probably mostly sit with those agents. But the EVs or their charging points would need to have enabled this sort of smart control. So, time delay of charging, etc. So I would say that would probably be the way to organize this.
Any other questions? Yes.
Yes, please. Is there any concern about smart timing will impact the demand of the EV itself? That means the customers maybe they will be controlled about their timing of their charging will affect of owning actually these vehicles or not?
So will it affect what? Sorry?
The owning, they will buy or not?
How they're used, the vehicles?
No. If there will be control about the customers' time of charging their vehicles, maybe they will not buy it actually.
Oh, I see. So how would that affect the ownership or the decision to buy the vehicle? We didn't study that here, so as I said, we just assumed that there's a certain amount of vehicles around. However, within this Green Motion project, there was there was a report on the customer acceptance and behavior related to EVs, and as part of that, there was a big survey carried out on probably a few thousand participants that answered, and that survey, it's not just a classical survey, it's what's called a stated choice survey. So what it tried to estimate is how much value different customers put on different attributes of the cars. Of course, price being probably the key one, but also this price or the cost of ownership will be affected if we have proper mechanisms in place. It will be affected by whether we do it smartly or not. And so there are some questions in that survey which touched upon this subject of whether you would be willing to participate in the smart schemes or not. So if you're interested in more, that was I think done by the Danish Technical University, their transport engineering department. There will be some more information there.
Can I ask a slightly different question? To what effect do you think seasonality has an impact? I mean, in some European cities, for example, they empty out in August for people leave to go on holiday. Consequently, they're using electric vehicles, maybe demand pops up somewhere else.
Yeah.
Was that considered in your work, and do you think it would have an effect as well?
Unfortunately, we couldn't go into such details. We did consider the seasonality in terms of that you would expect that the consumption of electricity, the specific consumption per kilometer will probably be higher in winter. That of course, this is a European situation, so because of heating, you would probably consume more electricity during winter. Then in the kind of spring and autumn season, you would consume less, and then in the summer you would consume more, again, slightly more because of the air conditioning. So we took this into account, but we didn't model the kind of migration between different regions. Although probably worth saying that when it comes to the cost, or when it comes to reinforcing this distribution grid, the probably critical period is the winter work day. So and during that season, you might expect that most people are around, and that's when the network is most stressed. Whereas summer, at least in Europe, at least in kind of moderate climate Europe, you wouldn't see a larger loading of the grid in the summer, with probably the exception of the southern countries like Spain and Italy or Greece. But mostly it's the winter peak that's we would need to worry about.
Last question in the back.
What I understand from the solution providers are giving the consumer the option between choosing a time filling or time-based charging and on-time charging. That means this charging time can be delayed, according to the system. So is that clear? That's as an option to the consumer to choose between these two options. And the second question is what the real difference between the smart and fully smart? In the presentation you chose us. And this smart solution can be better to be adopted by the service provider or infrastructure provider. An example, this solution not on the electric vehicle. So I have three questions for that.
Okay, I'll try to answer. I hope I understood it correctly. So the first question was about whether it's the consumer that will have the option of choosing smart or non-smart. And yes, essentially that will boil down to that. No one will be able to force you as a consumer to choose whether your demand could be delayed or not. It's only that your decision to do that or not.
So why, how I will make the consumer choose this option?
I'll come to that.
Yeah.
The primary mechanism will be cost, of course. So if I want to choose whatever I want, that might cost me, say, 3 times more, 5 times more than charging at the times which are the best for the system. So that would be one potential incentive, rather than having a direct control. So the consumer would have the end choice, of course. So some people might value their comfort so much that they would be willing to pay more just because they can't be bothered to wait for the car to be charged. They just want it now, here and now. But the majority of users would expectedly have some sensitivity, at least, to the cost of their electricity, so they would probably go for some degree of smartness. But that's again the question of implementation that we didn't look at, but all these are of course very relevant for the policy, for the